It's easy to think of space as empty. When you look up at the night sky, all you see is darkness sprinkled with pinpricks of light. But those stars are just the tip of the cosmic iceberg. Between the orbits of Earth and Mars alone, astronomers have found more than 200 billion stars, almost one for every person on the planet. Most of them are small, dim red dwarfs, and in a few trillion years they will begin to die. But death is not an ending, it's a transformation. Those dying stars will not disappear, but instead become something new. They will become white dwarfs, the silent stellar corpses that hold the memories of entire galaxies. To understand how these stellar corpses are made, let's take a quick tour through the life cycle of a star like our Sun. Stars shine by fusing hydrogen into helium in their cores. This nuclear fusion powers everything from the smallest red dwarfs to the largest blue giants. But it's also the key to their eventual demise. As a star like our Sun fuses hydrogen, it gradually builds up a core of helium. Eventually, the core becomes so massive that it collapses, crushing helium atoms into carbon. If the star were massive enough, this process would continue until iron is formed in the core. At that point, the star has exhausted its nuclear fuel and its end is near. Some stars will explode in one final act of fusion, scattering their outer layers into space in a spectacular supernova. Others will collapse under the pull of their own gravity, crushing themselves into unimaginably dense objects called black holes. But most stars, including our Sun, will not meet such a dramatic end. They will simply fade away. As a star like our Sun exhausts its supply of hydrogen, it will gradually cool and its outer layers will expand, turning it into a red giant. Eventually, the star's core will become a white dwarf. The red giant phase might be dramatic, but astronomers don't actually observe too many stars going through it. That's because most stars are much smaller than our Sun, and for very small stars, the transition to a red giant is both slow and subtle. In fact, most astronomers do get to see stars like our Sun die, because it takes tens of trillions of years to reach the white dwarf stage. The oldest stars in the universe are only about 13.8 billion years old, so basically no one has witnessed the death of a star like our Sun. But astronomers can study white dwarfs to piece together what happened. White dwarfs are incredibly dense, packing around 90% of a star's mass into a sphere the size of Earth. That means a teaspoon of white dwarf. Material weighs around 200 million pounds, or roughly the same as 200 of us. White dwarfs also come in a variety of sizes. Some are barely bigger than Earth. Others, known as ultra-cool white dwarfs, are around the size of Jupiter. The size of a white dwarf, when it forms, depends on the mass of the star that exploded into it. More massive stars make more massive white dwarfs. Astronomers believe that white dwarfs can also gain mass by consuming material from a nearby star. But exactly how white dwarfs form and evolve is still a mystery. That's partly because they are so dim. When they first form, white dwarfs are incredibly hot. Surface temperatures ranging from 4,000 to 40,000 degrees Fahrenheit. That heat makes them visible to telescopes like the James Webb Space Telescope. But because white dwarfs are so small, they cool off pretty quickly. Within a few million years, they become too cold to be seen by telescopes. There are a few exceptions. The hottest white dwarfs emit X-rays that can be detected by special telescopes. But most of them are now invisible. Some astronomers think that white dwarfs might be detectable by studying the light from nearby stars that pass in front of them. But these opportunities are rare. And so for now, white dwarfs remain largely out of sight and out of mind. Yet despite their dimness, white dwarfs are everywhere. You can find them drifting through the galaxy like lonely ghosts, each one a silent witness to the history of cosmic evolution. And as our technology improves, astronomers are finding ways to study them in more detail. In the future, they hope to use white dwarfs to better understand our universe, to date the oldest galaxies, test fundamental physics, and learn more about exoplanets. And most significantly, white dwarfs offer a glimpse of our own Sun's ultimate fate. So next time you look up at the night sky, remember that twinkling point of light up there. In a few trillion years, it too will fade to become a white dwarf, joining the vast stellar graveyard that surrounds us. Death is not an ending, it's a transformation. The stars may fade, but their story doesn't end there. Every star begins its life in a cloud of gas and dust. Gravity pulls the particles together, causing the cloud to collapse and heat up. When the core reaches around 10 million degrees Celsius, nuclear fusion ignites. Hydrogen nuclei fuse into helium, releasing energy that counterbalances gravity's relentless pull inward. This balance between gravity trying to crush the star and fusion pushing outward is what allows stars to exist in stable equilibrium for billions of years. But what happens when the fuel runs out for massive stars, those more than about 8 times the mass of our Sun? The ending is explosive. They collapse and detonate as supernova, leaving behind neutron stars or black holes. But the majority of stars in the universe, the smaller ones, die quietly. Their path does not end in violence, but in exhaustion. Let's take the Sun as an example. It has been fusing hydrogen in its core for 4.6 billion years, and will continue to do so for about another 5 billion years. When the core hydrogen is exhausted, gravity begins to squeeze the star. Meanwhile, fusion shifts to a shell around the core. The outer layers expand dramatically, and the star transforms into a red giant. The Sun's radius will balloon to hundreds of times its current size, potentially engulfing Mercury and Venus, and possibly even Earth. Inside this swollen red giant, the core becomes hotter and denser until helium fusion begins. Helium fuses into carbon and oxygen, creating a dense heart at the center. But here lies the crucial difference between low-mass and high-mass stars. Stars like the Sun never become hot enough to ignite carbon fusion. They reach a dead end. When the helium runs out, the star has nothing left to burn. Its outer layers are blown away into space, forming a planetary nebula, a shell of glowing gas that drifts off into the interstellar medium. At the center remains the exposed core, a hot, Earth-sized object composed mostly of carbon and oxygen, no longer powered by fusion, but supported against collapse by a strange quantum force called electron degeneracy pressure. This remnant is the white dwarf. Here, quantum mechanics steps in to prevent complete destruction. In normal matter, electrons can move freely within atoms, but they cannot all occupy the same energy state. This principle, known as the Pauli exclusion principle, creates a pressure that resists further compression. Unlike normal thermal pressure from fusion, this degeneracy pressure does not rely on heat. It is purely a quantum effect, and it is what keeps a white dwarf from collapsing under its own gravity. Thus, a paradoxical object is born. Incredibly dense yet stable, cold yet still faintly glowing with leftover heat, dead yet enduring for trillions of years. White dwarfs packed extraordinary physics into tiny scales. The Sun, for instance, will one day shrink from its current size, 1.4 million kilometers across, to a sphere no larger than Earth, about 12,000 kilometers in diameter, yet it will retain around half its present mass. Imagine compressing the weight of the Sun into the size of our planet. A single teaspoon of white dwarf material would weigh several tons on Earth. The formation of white dwarfs is not a rare or exotic outcome. It is the default fate of stars. From the humble red dwarfs scattered throughout the Milky Way to stars a few times the mass of the Sun, most will walk this evolutionary path. The seemingly endless array of stars twinkling above us is, in fact, filled with stars destined to become white dwarfs, the final, quiet stage of stellar evolution for the vast majority of the cosmos. By tracing this pathway, we not only understand where stars go when they die, but also where our Sun is headed. The white dwarf phase is not a curiosity at the margins of astrophysics. It is the story of stellar destiny written across the universe. The Sun, along with countless other stars, will one day shed its outer layers, revealing a hot, dense core, a white dwarf. And although some may find this ending anticlimactic, in a universe brimming with cosmic drama, this quiet fade into a white dwarf is, in many ways, the most fitting conclusion for a star. It is a testament to the power of physics to create objects of such density that they defy our expectations. And it is a reminder that even as stars die, they leave behind remnants that continue to fascinate and teach us about the universe we inhabit. If white dwarfs are so common, why do they still feel so mysterious? Part of the answer lies in their nature. They are small, faint, and difficult to see. Detecting one against the glare of its parent star, or in the vastness of space, requires extraordinary precision. And yet, a handful of white dwarfs have become iconic in astronomy, not only because they were among the first discovered, but because they continued to teach us about the fundamental physics of the universe. In this episode, we will focus on a few white dwarfs that stand out for the unique contributions they have made to our knowledge. While there are many more worthy mentions, time constraints limit us to a small selection. Our journey begins with Sirius B, the first white dwarf recognized as such. Sirius is located 8.6 light-years away in the constellation Canis Major. To the naked eye, now it's the brightest star in the night sky, shining nearly twice as bright as the next brightest Procyon. But that apparent brightness is partly because Sirius has a close companion. In 1844, German astronomer Friedrich Bessel noticed something odd. While studying Sirius, he saw that the star wasn't sitting still. It was wobbling slightly in its path, like a celestial game of cosmic billiards where Sirius A was gently nudging Sirius B now. You might wonder, why didn't they notice this before? Well, until the 1800s, telescopes weren't advanced enough to measure such minute movements. With painstaking observations and calculations, Bessel concluded that the unseen companion must be at least as massive as Jupiter. He couldn't see it directly because, get this, it was too small and dim. It was invisible to telescopes of the time. However, the clues were there if one knew where to look. A couple of decades passed before someone did. Enter Alvin Graham Clark, an American telescope maker who crafted his own instruments in the 1860s. On January 31, 1862, while observing Sirius, Clark noticed a tiny point of light near its larger companion. Eureka! Finally, Sirius B was seen. And what they found was nothing short of astonishing. Sirius B was a small star, roughly the size of Earth, but packed the same mass as the Sun. How could this be possible? Scientists had theories about white dwarfs, but nothing could explain this tiny, dense object. It was almost as if a giant had taken a star and squeezed it into a tiny space. They needed a new understanding of physics to make sense of it. Fast forward to today, Sirius B remains one of the most researched white dwarfs, largely due to its proximity. Astronomers know its distance accurately and can watch it change over time. The star is about 25,000 kelvins hot, meaning it glows in the ultraviolet part of the spectrum. And yes, it is cooling, but at a snail's pace. According to calculations, it will take several billion years to reach room temperature. Sirius B has helped astronomers understand how matter behaves under extreme conditions. They can check whether models of matter under high pressures match what they observe in the star. Additionally, the binary system gives astronomers an opportunity to gauge the mass of the white dwarf. Knowing both its mass and radius helps them refine models of stellar evolution and test general relativity. Next up, let's talk about the ZZ Ceti stars. These peculiar stars are also known as pulsating or variable white dwarfs. And you might be thinking, why would any astronomer want to study something that fluctuates all the time? Well, it turns out that these wobbles are incredibly informative. Imagine you hear a musical note and you can tell the number of vibrations per second. That's the frequency. This simple observation tells you something about the object that produced the sound. Similarly, white dwarfs have a natural vibration rate that depends on their size and mass. By tracking these pulsations, astronomers learn about the internal structure of the star. But it gets better. Different parts of a star can vibrate independently, much like when you play different notes on a piano. In 1961, researchers identified the first ZZ Ceti star, and soon after, they noticed that these stars don't just pulsate, they emit light in a periodic fashion as well. This behavior led to the discovery of non-radial pulsations, meaning the star expands and contracts in complex ways rather than just up and down. It's like a star winking at us in its own unique code. Over the years, astronomers have spotted various pulsation modes in ZZ Ceti stars. By analyzing these oscillations, they gain insights into the star's internal structure. It's like having a window into the star's beating heart. Moreover, the study of ZZ Ceti stars goes beyond individual objects. It offers a way to probe stellar populations. For instance, some ZZ Ceti stars exhibit helium in their atmospheres, a sign of a binary system where the white dwarf has gained mass from its partner. By identifying and studying these stars, astronomers learn about the prevalence of such systems and gain a broader perspective on stellar evolution. Moving on, let's explore a class of white dwarfs known as DB and DQ stars. Unlike most white dwarfs, which have a hot, glowing atmosphere, these stars display strong ultraviolet absorption lines of heavy elements like iron. But wait, how do they keep these elements in their atmosphere? Normally, these elements should sink to the core due to gravity. Well, that's where things get interesting. DB and DQ stars rotate rapidly, whipping matter away from their surfaces in a process called spin-driven mass loss. This creates an outward force that counteracts gravity, keeping the heavy elements in the atmosphere. And here's where it gets really fascinating. As these stars lose mass, they rotate faster, heating up their surfaces. It's a delicate balance between centrifugal force, gravity, and radiative cooling. Astronomers use sophisticated computer models to study how these factors interact, and it's a cosmic balancing act that reveals the true nature of stellar remnants. Now let's shift our focus to a remarkable white dwarf named Stein 2051. This star is the hottest white dwarf ever discovered with a staggering surface temperature of over 200,000 Kelvin. To put that in perspective, the Sun's photospheric temperature is about 5,800 kelvins. What makes Stein 2051 so scorching hot? The answer lies in its youth. It's a mere 300 million years old, which is baby stuff in astronomical terms. Most white dwarfs are ancient, cooling remnants of long-lived sun-like stars. However, Stein 2051 is an exception, formed in a young open cluster known as the Beehive cluster. Its high temperature suggests that it recently shed its hydrogen-rich outer layers, revealing the hot, glowing carbon core beneath. Studying Stein 2051 gives astronomers a glimpse into the early stages of stellar evolution, helping them understand the processes that shape a star's destiny. We can't forget to mention some notable white dwarfs in our own galactic neighborhood. One such star is Procyon B. Discovered in the 19th century, its white dwarf orbits the bright star Procyon A. Then there's Van Manen star, a nearby solitary white dwarf first identified in 1917. And let's not forget LP42 365, a unique white dwarf thought to be the remnant of a failed supernova explosion. It moves through space at an impressive speed of 216 kilometers per second, providing clues to its violent past. These white dwarfs, often overlooked, hold secrets that help us understand our place in the cosmos. They offer glimpses into stellar evolution, the physics of matter, and the dramatic events that shape galaxies. White dwarfs may appear simple, small, cooling, stellar remnants slowly fading into darkness. But beneath their quiet exterior lies a frontier of astrophysical mysteries. They are extreme environments where quantum mechanics, relativity, and even cosmology collide. Two of the greatest puzzles linked to white dwarfs involve their crystallization and their potential interactions with dark matter. The crystallizing star, imagine a star turning into a diamond. This is not poetic metaphor, but physical reality. As white dwarfs cool, the carbon and oxygen nuclei inside them begin to settle into ordered, lattice-like structures. This process, crystallization, is the same principle by which water freezes into ice, except here it occurs at densities millions of times higher. In 2019, astronomers using data from the Gaia spacecraft identified vast populations of white dwarfs that were in the midst of crystallizing. They discovered a pileup in the Hertzsprung-Russell diagram, essentially a cluster of stars lingering longer at certain temperatures, consistent with the release of latent heat as their interiors froze into solid crystal. What does this mean? It means that many white dwarfs in the galaxy are not just cooling embers, but solidified stars, giant spheres of crystalline carbon and oxygen. In a sense, the Milky Way may already be filled with stellar diamonds the size of Earth. For astrophysics, crystallization is more than a curiosity. It provides a natural clock for stellar aging. Because crystallization releases heat, it delays cooling. By measuring which white dwarfs are crystallizing and comparing them to models, astronomers can estimate the age of the galactic disk, helping to date the history of the Milky Way itself. Another puzzle involves the mass limit. All matter has a delicate balance between opposing forces. Gravity pulls inward while electron degeneracy, pressure pushes outward. For a white dwarf, this balance holds against gravitational collapse. But there's a limit. If a white dwarf exceeds about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, electron degeneracy pressure fails, gravity wins, and the star collapses further, usually exploding as a Type Ia supernova. But not all white dwarfs fit neatly into this model. Some seem to hover just below the limit with unusual stability. Others, in binary systems, gain mass from companions and trigger supernova at slightly different thresholds. Astronomers are still working to understand these phenomena. They're trying to pin down when, why, and how these explosions occur. Not only because they are fascinating stellar events, but because Type Ia supernovae are used as standard candles for measuring cosmic distances. Any uncertainty in their white dwarf origins ripples into our understanding of the expansion of the universe. Then comes perhaps the most tantalizing speculation. Could white dwarfs reveal the nature of dark matter? Dark matter, the invisible mass making up about 85% of the universe's matter, remains one of physics' greatest unsolved mysteries. If dark matter particles exist, they may occasionally collide with ordinary matter. White dwarfs, with their extreme density and long lifespans, are perfect detectors for such rare events. Here's how. If dark matter particles interact inside a white dwarf, they could either add energy, subtly heating the star, or trigger runaway collapse. If enough dark matter collects in the core, some theories predict that dark matter interactions could cause premature explosions resembling Type Ia supernova. Astronomers are actively studying the cooling rates of white dwarfs to test this idea. If white dwarfs are cooling slower or faster than models predict, it could be evidence of exotic interactions, a cosmic whisper from the dark matter that pervades the galaxy. In essence, white dwarfs are astrophysical laboratories, allowing us to study matter in extreme conditions that we cannot recreate on Earth. The fact that they exist at all is something of a triumph for astrophysics. Before the 1960s, theorists did not believe that stars could shed their outer layers and leave behind such compact remnants. But observations revealed that they were wrong. Today, studying white dwarfs helps resolve issues that span multiple areas of physics. Just consider the progress made in recent years. In 2012, researchers announced the discovery of the first binary system with a white dwarf in one of its components. Shortly after, in 2013, scientists confirmed the existence of the first planet orbiting a white dwarf. Then in 2016, analysis of a white dwarf atmosphere provided the first observational evidence of the proton, a subatomic particle considered one of the building blocks of matter. And in 2019, a joint project between the European Space Agency and NASA provided the first detection of an object orbiting a white dwarf that was not a planet but a black hole. Such discoveries drive progress across various fields, including nuclear physics, particle physics, and general relativity. To unravel these mysteries, scientists employ a range of techniques. Spectroscopic analysis of starlight passing through a star's atmosphere reveals its chemical composition and temperature. Astronomers also observe periodic changes in brightness in binary systems, where a white dwarf S-light is periodically blocked by an orbiting object, providing insights into both the white dwarf and its companion. Gravitational microlensing is another powerful tool. As a white dwarf briefly passes in front of a more distant star, its gravity magnifies the starlight, creating a temporary brightening that can reveal otherwise unseen objects in the system. This technique has been instrumental in discovering planets around white dwarfs. Furthermore, advanced computer simulations allow scientists to model the behavior of matter under extreme conditions found in white dwarfs, testing and refining theoretical predictions. As technology advances, our ability to probe these stellar remnants will continue to improve. Upcoming space-based telescopes promise to detect and characterize exoplanets around white dwarfs in greater numbers, shedding more light on these diverse systems. Ground-based observatories are also making strides. For example, the high-energy spectrograph on the Subaru telescope in Hawaii is designed to study white dwarfs and other celestial objects across a wide range of wavelengths, enabling researchers to delve deeper into their properties. One particularly intriguing area of research involves searching for signatures of dark matter within white dwarfs. This unconventional approach stems from the fact that white dwarfs are primarily composed of ordinary matter, making them susceptible to hypothetical interactions with dark matter particles. If these interactions occur within a white dwarf, they could manifest as subtle variations in the star's temperature or even hint at a runaway collapse. By analyzing data on white dwarf cooling rates and exploring potential correlations with dark matter, Scientists hope to shed light on the nature of this elusive substance. Another active area of investigation focuses on understanding the formation and evolution of planetary systems around white dwarfs. Observations of exoplanets orbiting these stars have revealed a surprising diversity of worlds, including some with atmospheres similar to Earth's. Studying these systems provides valuable insights into the complex processes that shape planetary systems over time. Additionally, astronomers are continuously refining their understanding of the role white dwarfs play in the broader context of stellar evolution. By examining the properties of white dwarfs and their progenitors, they aim to reconstruct the life cycles of stars and shed light on the pathways that lead to the formation of these compact remnants. In summary, the study of white dwarfs represents a dynamic and multifaceted area of astrophysical research. From probing the fundamental nature of matter to exploring the diversity of planetary systems and understanding stellar evolution, these stellar remnants offer a rich tapestry of scientific inquiry. As technology advances and observational capabilities improve, astronomers are poised to unravel the secrets held within these enigmatic objects, potentially leading to groundbreaking discoveries that challenge our current understanding of the universe. On the brink of new missions dedicated to exploring our closest stars, scientists are eagerly anticipating fresh perspectives on these celestial enigmas. Among the most anticipated projects is the Nancy Grace Roman Space Telescope, an upcoming mission by NASA and the Canadian Space Agency set to launch in the mid-2020s. This telescope is equipped with a wide-field instrument that will enable it to survey a substantial portion of the Milky Way, providing an unprecedented view of nearby stars and their systems. With its advanced instruments, the Roman telescope will have the capability to detect and characterize exoplanets around white dwarfs in greater detail than ever before. By observing these systems, scientists anticipate gaining insights into the formation and evolution of planets in extreme environments. Another exciting development is the Lisa Lavoie joint venture between the European Space Agency and the Chinese Space Agency, set to launch in the late 2020s. This mission will focus on detecting gravitational waves, ripples in space-time caused by the acceleration of massive objects. LISA will be particularly sensitive to signals from compact binary systems, including those involving white dwarfs. By detecting gravitational waves emitted by merging white dwarfs, LISA will provide unique information about their masses, distances, and internal properties. These observations will complement those from other telescopes and missions, offering a more comprehensive understanding of white dwarf systems. Let's not forget about the James Webb Space Telescope, an ambitious project led by NASA in collaboration with the European Space Agency and the Canadian Space Agency. Although not primarily focused on white dwarfs, the Webb telescope will make significant contributions to the field. Its infrared capabilities will allow it to observe objects that are too faint or distant for visible light telescopes, including young white dwarfs and those in distant galaxies. By peering into the infrared, Webb will help unveil the chemical properties of white dwarf atmospheres and shed light on their role in the early stages of galaxy formation. As these missions approach launch, the scientific community eagerly awaits the new perspectives and discoveries they will bring. Each mission is equipped with state-of-the-art instruments and detection methods poised to revolutionize our understanding of white dwarfs and their place in the grand scheme of the universe. When combined, their findings will paint a more complete and intricate picture of these fascinating stellar remnants, pushing the boundaries of human knowledge and inspiring future generations of astronomers. In the grand tapestry of the cosmos, few subjects resonate as profoundly as the concept of time. Yet here we are, poised on the brink of unraveling the intricate details of a celestial spectacle, so vast and awe-inspiring that it defies the boundaries of human comprehension. Brace yourself for a journey through time as we delve into the secrets of a white dwarf. Join us as we navigate the labyrinthine passages of this stellar remnant, shedding light on its composition and unveiling the tantalizing questions that surround it. But before we embark on this cosmic odyssey, we invite you to join our community of space enthusiasts. Your support fuels our passion and enables us to continue sharing these captivating tales of the cosmos. Prepare to be captivated as we explore the very essence of a white dwarf, delving into its formation and uncovering the mysteries that shroud its birth. Our solar system stands as a celestial stage where the sun takes center stage, radiating its brilliance and keeping our planet in its harmonious embrace. But have you ever pondered what might lie in store for our sun when it reaches the twilight years of its existence? Picture a sun stripped of its outer layers, leaving behind a dense, hot core that glows with an eerie white light. This enigmatic remnant is none other than a white dwarf. It serves as a celestial time capsule, encapsulating the sun's evolution and offering clues to its ultimate fate. To comprehend the birth of a white dwarf, we must first grasp the life cycle of a star. Stars are born in colossal clouds of gas and dust, known as nebulas, and our sun is no exception. As gravity orchestrates a cosmic ballet, these celestial bodies collapse, igniting nuclear fusion in their cores. Hydrogen transforms into helium, releasing tremendous energy that propels the star towards maturity. Our sun has gracefully danced through this evolutionary journey, steadily fusing hydrogen into helium for billions of years. Yet as the supply of available hydrogen dwindles, the star's life enters a precarious balance. Gravity, relentless in its pursuit, begins to overpower the outward push of nuclear fusion. The star's core contracts, heating up the surrounding hydrogen until it ignites. It's causing the star to expand dramatically. This marks the sun's transition into a red giant, a phase characterized by its immense size and cooler surface temperature. As the sun embarks on this new chapter, its core continues to shrink. With the core of helium increasing in temperature and pressure, eventually, conditions become so extreme that helium itself succumbs to nuclear fusion, giving rise to carbon and oxygen. With helium exhausted, the sun finds itself at a critical juncture. Its core, composed of inert carbon and oxygen, can no longer support nuclear fusion. Gravity asserts its dominance, causing the outer layers of the star to drift away into the vast expanse of space. This ethereal cloud of gas and dust forms a magnificent spectacle known as a planetary nebula, leaving behind the sun's dense core. This core, stripped of its outer layers, reveals a scorching hot Earth-sized object, a white dwarf. Now that we've traced the birth of a white dwarf, let's turn our attention to its composition, a topic that has puzzled astronomers for centuries. At the heart of a white dwarf lies a core composed of highly compressed carbon and oxygen. This core, though small in size, boasts a mass comparable to our sun. Imagine a sphere roughly the size of Earth, yet containing a mass equivalent to the sun. Such density defies earthly comparisons, making a white dwarf one of the most compact stellar remnants in the universe. But the journey through the composition of a white dwarf doesn't end there. Surrounding the core is an enigmatic atmosphere, a thin veil that cloaks the true nature of this celestial enigma. The atmosphere of a white dwarf is primarily composed of hydrogen and helium, elements that were once abundant in the star's outer layers. However, the intense gravity of the white dwarf causes these elements to accumulate near the star's surface, forming a delicate balance. These elements are not merely present as single atoms, but exist as ionized gases, stripped of their electrons, due to the extreme temperatures and pressures that permeate the white dwarf's vicinity. For instance, helium exists as He2, indicating that each helium atom has lost one of its 2 electrons. Similarly, hydrogen is found as H, signifying that each hydrogen atom has shed its lone electron. This ionization creates a sea of charged particles around the white dwarf, forming an electrically neutral plasma. The interplay between these ionized gases gives rise to a dazzling display of astronomical phenomena. One such phenomenon is the ubiquitous white dwarf D, a spectral feature that has intrigued astronomers for decades. This mysterious line in the ultraviolet portion of the electromagnetic spectrum serves as a telltale sign of the ionized helium found in white dwarf atmospheres. Its presence provides astronomers with a valuable tool to study the composition and properties of these enigmatic stars. Additionally, the atmosphere of a white dwarf is often enriched with heavier elements, including carbon, oxygen, and even iron. These elements were forged in the star's core during its lifetime and were subsequently expelled during the planetary nebula stage. The presence of these elements adds another layer of complexity to the study of white dwarfs, providing insights into the stellar nucleosynthesis that occurred during the star's existence. As we continue our exploration of white dwarfs, we encounter another intriguing aspect: their magnetic fields. Unlike their more familiar cousins, neutron stars and black holes, white dwarfs typically possess relatively weak magnetic fields. These magnetic fields are thought to originate from the star's convective outer layers, where plasma motions generate electric currents. However, the exact mechanism by which these magnetic fields are amplified and structured remains shrouded in mystery. Understanding the origin and behavior of these magnetic fields is crucial for unraveling the complexities of stellar winds and accretion processes that shape a white dwarf's evolution. But the journey through the composition of a white dwarf does not end here. There is much more to uncover about this celestial enigma. White dwarfs are often classified based on their surface gravities, with the most common types being dA, dB, and dQ. dA white dwarfs have surface gravities above 10 raised to the power of 5 centimeters per second squared. dB and dQ white dwarfs have lower surface gravities. The differences in surface gravities reflect variations in the composition and structure of the white dwarf's atmosphere. Each classification provides astronomers with a unique window into the star's evolution and its interaction with its surroundings. By studying these different types of white dwarfs, scientists gain valuable insights into the diverse range of processes that occur in these fascinating objects. White dwarfs are not just celestial curiosities. They play a significant role in shaping our understanding of the universe. By studying these enigmatic remnants, astronomers gain insight into stellar evolution, the life cycle of stars, and the processes that govern their demise. Moreover, white dwarfs serve as testing grounds for theories of nuclear physics and astrophysics, allowing scientists to probe the fundamental laws of the cosmos. White dwarfs also offer a glimpse into the fate of our own sun. By studying these remnants, astronomers can better predict what will happen to our star when it reaches the end of its life. This knowledge helps us appreciate the transient nature of celestial objects and the dynamic processes that shape our universe. Furthermore, white dwarfs have implications for exoplanet research. By analyzing the light that passes through the atmospheres of white dwarfs, astronomers can detect and characterize exoplanets that orbit these stars. Studying exoplanet systems around white dwarfs provides valuable insights into planetary migration, atmospheric composition, and the diversity of planetary systems in our universe. In conclusion, white dwarfs stand as silent sentinels in the vast expanse of the cosmos, preserving the secrets of stellar evolution and nucleosynthesis. Their enigmatic nature continues to captivate astronomers, driving them to unravel the mysteries that surround these celestial remnants. As we continue to explore the depths of space, white dwarfs will undoubtedly remain a focal point of scientific inquiry, guiding us toward a deeper understanding of the universe and our place within it. White dwarfs may be silent, but they have spoken volumes to humanity. Their discovery and study have not only expanded our knowledge of the cosmos, but also tested the very limits of physics. To understand how we came to know them, we must look at the astronomers, physicists, and instruments that brought these strange objects into focus. Early discoveries and the mystery of density. When Sirius B was discovered in 1862, it seemed paradoxical. A star as massive as the Sun, but no bigger than Earth. Early estimates of its density were shocking. Hundreds of thousands of times denser than water. 19th century physics? This made no sense. How could matter be so compressed? At the time, the tools of quantum mechanics and relativity did not yet exist. The nature of white dwarfs was an unsolved riddle, waiting for a revolution in science. That revolution began in the early 20th century, when quantum mechanics introduced the idea of electron degeneracy pressure. This strange quantum-based pressure explained how a star could resist collapse without fusion. But the story didn't end there. In 1930, a young Indian physicist named Subramanian Chandrasekhar boarded a ship from India to England. On the voyage, he worked through equations describing the balance of electron degeneracy, pressure, and gravity in white dwarfs. What he found was astonishing. There is a limit to how massive a white dwarf can be. If a white dwarf exceeds about 1.4 solar masses, now known as the Chandrasekhar limit, electron degeneracy pressure can no longer hold it up. The star must collapse further into a neutron star or black hole. At first, his conclusion was met with skepticism. In fact, the famous astrophysicist Arthur Eddington publicly dismissed Chandrasekhar's work, calling it absurd. For years, Chandrasekhar's result was debated, resisted, and questioned. Yet time proved him right. His calculations became foundational to modern astrophysics, shaping our understanding of stellar evolution, supernova, and compact objects. In 1983, Chandrasekhar received the Nobel Prize in Physics for this pioneering work. The Chandrasekhar limit remains one of the cornerstones of astrophysics today, governing not only white dwarfs but also the origins of Type Ia supernova, the very explosions that allow us to measure the expansion of the universe. The Hubble Space Telescope and white dwarfs of Chandrasekhar gave us the theory. Telescopes like Hubble provided the evidence. Launched in 1990, the Hubble Space Telescope transformed the study of white dwarfs. With its sharp vision above Earth's atmosphere, Hubble could observe faint stars and resolve binaries that ground-based telescopes could not. Hubble made direct measurements of white dwarf masses, confirmed their cooling rates, and even provided some of the first detailed spectra of white dwarfs. Most famously, Hubble helped refine the white dwarf cooling sequence, the predictable way these stars fade with time. By measuring white dwarfs in globular clusters, astronomers used them as cosmic clocks, estimating the ages of some of the oldest stellar populations in the galaxy. Gaia in the modern era today, the Gaia mission, launched by the European Space Agency, is carrying the torch. By mapping over 1 billion stars with unprecedented precision, Gaia has revealed entire populations of white dwarfs, their positions, motions, and even signs of crystallization. Where Chandrasekhar's equations gave theory, Gaia provides an atlas of reality. The human side of ghost stars, the journey from the discovery of Sirius B to the Nobel-winning insights of Chandrasekhar, to the breathtaking images from Hubble and Gaia, is a testament to human curiosity. White dwarfs may be quiet, but they have inspired some of the loudest advances in science, in quantum physics, relativity, and cosmology. They show us how deeply intertwined human history is with cosmic history. A young physicist working on a ship, a telescope orbiting Earth, a satellite mapping stars across the galaxy, all converging on the same truth. Even dead stars have stories to tell. As we continue to explore the cosmos, we are driven by an insatiable curiosity. White dwarfs, once thought to be mere oddities, have become keystones in our understanding of stellar life cycles and the physics of extreme environments. They serve as a reminder that even in the coldest, densest stellar remnants, there is something profoundly beautiful and deeply humbling. The more we learn about white dwarfs, the more they reveal about the universe and our place within it. So as we gaze up at the stars, let us not only marvel at their beauty, but also celebrate the tireless spirit of exploration that drives us to uncover their secrets. Who knows what other wonders and revelations await us in the vast expanse of the cosmos? Perhaps there are even more stories waiting to be told by the silent stars. White dwarfs are dead. Our nuclear furnaces have gone out, their bloated outer layers thrown away. All that remains is a scorching hot, Earth-sized core of degenerate matter, no bigger than a handful of dust. But what if these stellar corpses hold the keys to a universe reborn? Astronomers are learning that white dwarfs are more than just the graves of stars. They are some of the most valuable tools in astrophysics, allowing us to probe the history of the Milky Way, imagine the deep future of the universe, and confront some of the biggest questions in cosmology. If white dwarfs are the silent corpses of stars, then they are also the timekeepers of the galaxy. Their predictable cooling makes them some of the most valuable tools in astrophysics. By measuring the temperature of a white dwarf and comparing it with models of cooling, astronomers can estimate its age. This has profound consequences. In globular clusters, which are among the oldest structures in the galaxy, astronomers have measured white dwarfs to determine that many clusters are over 12 billion years old. These measurements help place limits on the age of the Milky Way itself, providing independent checks against cosmological models. White dwarfs, in other words, are not only stellar remnants, they are chronometers, marking the passage of cosmic time. The future of white dwarfs is uncertain, but their past is clear. Once white dwarfs form, they cool slowly. How slowly? Well, that depends on several factors. One is their mass. Heavier white dwarf will cool off more slowly than a lighter one, because a greater mass means a greater gravitational pull that keeps the star's core hotter for longer. Another factor is the presence of an atmosphere. If the white dwarf has an outer layer of material, It will cool off more quickly due to the exchange of energy between the two phases. Finally, there's the composition of the atmosphere and core. A pure carbon atmosphere, for instance, would cool more quickly than one containing oxygen. Astrophysicists use computer models to simulate the complex interplay of these variables. These models incorporate fundamental physical processes, including radiation, convection, and the behavior of degenerate matter. By adjusting model parameters, scientists try to match the predicted cooling curve with observations of real white dwarfs. The agreement isn't perfect, and this discrepancy motivates further study. There may be new physics at play that improves our models and gives us better clocks. For example, the cooling curves of some extremely old white dwarfs seem to flatten out, suggesting that they might be stable in size and temperature. That would imply some unknown process is halting their cooling, a potential hint of physics beyond our current understanding. In addition to refining models, astronomers are searching for ever older white dwarfs to calibrate the cooling curve. The quest for the oldest white dwarfs takes us to globular clusters, tightly bound groups of stars held together by gravity. Globular clusters are among the oldest structures in the Milky Way, and they contain a high fraction of white dwarfs, because low-mass stars like our Sun take billions of years to exhaust their nuclear fuel. Thus, globular clusters are ideal places to find ancient white dwarfs. By studying these stellar relics, astronomers have determined that some globular clusters are more than 12 billion years old, dating back to within a few billion years of the Big Bang. Remarkably, the ages of these clusters, derived independently from white dwarf cooling, agree with the ages of the oldest stars in the universe, known as population 3 stars. This convergence provides strong evidence for the Big Bang model and paints a coherent picture of the early evolution of our galaxy. But looking back is only part of the story. White dwarfs also offer a window into the far future of the universe. As the cosmos marches relentlessly forward, white dwarfs will become more abundant and Earth-sized relics will dot the Milky Way. In trillions of years, white dwarfs will outnumber stars by a factor of 10 to 1, becoming the dominant stellar population. To understand this future, we must first consider the present. Our Sun, like most stars, will exhaust its hydrogen fuel in about 10 billion years, shedding its outer layers and leaving behind a white dwarf. Our solar system's rocky planets will survive the transformation intact, but their orbits will be altered by the Sun's shrinking. Eventually, Venus will be closest to the white dwarf, followed by Earth, Mars, Jupiter, Saturn, Neptune, Uranus, and finally, Pluto. It will feel like a cosmic game of stellar musical chairs. This reshuffle of planetary orbits reflects a deeper change in the nature of our solar system and the Milky Way as a whole. As the Sun shrinks, the habitable zone, the region where conditions are suitable for life as we know it, will shift inward towards Mercury. Eventually, Earth will drift out of this zone and become too cold to support life. For now, we occupy a temporary niche in the habitable zone during the twilight years of our solar system's main sequence. But in the far future, when the Sun ignites helium in its core, it will briefly re-expand and Earth will be scorched once more. However, this second chance for life will be short-lived. Ultimately, the Sun will cool into a cold, dark black dwarf. Now, any life surviving until then will face an icy doom. It might seem that our place in the universe is precarious, but white dwarfs can actually protect us. When stars explode as supernova, they launch powerful shockwaves into space. These shocks compress gas and dust, triggering star formation and enriching the interstellar medium with heavy elements. However, if a supernova occurs near Earth, it could strip away our planet's atmosphere and boil the oceans. Fortunately, white dwarfs typically form in binary systems, and their close companions can shield us from potential dangers. In such systems, a white dwarf either pulls material from a nearby star or receives material from its companion after it explodes as a supernova. In either case, the white dwarf acts like a cosmic bouncer, repelling any intruders that come too close. This protective effect has profound implications for the future of life in the Milky Way, as stars like our Sun exhaust their nuclear fuel and shrink into white dwarfs. They will gradually accumulate a thin atmosphere of captured material. Over billions of years, this atmosphere will become enriched with nitrogen and oxygen, the essential ingredients for life. In other words, white dwarfs will create a hospitable environment that enables life to flourish in the far future. Our cosmic bouncers will ensure that future civilizations have the resources they need to thrive. Some white dwarfs will retain atmospheres of hydrogen and helium, the primordial elements forged in the Big Bang. Studying these atmospheres allows astronomers to probe the chemical activity of matter under extreme conditions. Scientists are particularly interested in the behavior of hydrogen, which exists in a state called fully stripped. Fully stripped hydrogen lacks the electron cloud typically associated with chemical activity, making it chemically inert. However, recent research suggests that fully stripped hydrogen atoms can undergo a form of chemical bonding known as quantum tunneling. In this process, atoms tunnel through energy barriers that would normally prevent them from interacting. Quantum tunneling could explain the surprising stability of some white dwarf atmospheres, potentially enabling complex chemical processes that defy conventional understanding. Further investigation of these exotic states of matter could revolutionize our understanding of the fundamental laws of nature. There's a surprising twist to the story of planetary systems and white dwarfs. While most planetary systems will disperse as their stars evolve, some will remain intact even after their star goes out. This is because the gravitational influence of a white dwarf is significantly weaker than that of a main sequence star of the same mass. In other words, planets bound to a white dwarf won't be flung into interstellar space by their gravitational pull. As a result, some planetary systems may retain their orbits around white dwarfs for billions of years. These systems serve as time capsules, preserving the conditions and compositions that existed in the early days of the universe. By studying them, astronomers gain insights into the origins of the solar system and the conditions that prevailed in the early stages of cosmic evolution. Moreover, the discovery of extrasolar planets orbiting white dwarfs, known as WD 1856b, has raised intriguing possibilities. This planet, roughly twice the mass of Earth, orbits a white dwarf every 11 days, raising questions about its origin and composition. Did it form in situ around the white dwarf, or is it a captured object from a nearby system? Unraveling the mystery of WD 1856b could provide clues about the prevalence of exoplanets and the diversity of planetary systems in the Milky Way. As we conclude our journey through the realm of white dwarfs, we encounter an unsettling possibility. What if these stellar remnants hold the key to our own demise? Some theories propose that white dwarfs with their faint dim glow could trigger gamma-ray bursts, the most energetic explosions in the universe. If such events occur near Earth, they could blast our planet with lethal radiation, wiping out life as we know it. Gamma-ray bursts pose a chilling reminder of the fragility of life in the cosmos and the unexpected threats that lurk in the far reaches of space. Exploring this dark side of white dwarfs helps us understand the full range of phenomena that shape the universe and confront the existential challenges that lie ahead. In the grand tapestry of the cosmos, white dwarfs may seem like mere threads, but upon closer inspection, they reveal themselves to be vibrant tapestries of stellar evolution, cosmic timekeeping, and the very essence of our existence. As we continue to unravel their mysteries, we uncover not just the secrets of dead stars, but the story of our universe and our place within it. From the ancient globular clusters to the distant reaches of space, white dwarfs stand as silent sentinels, guiding us toward a deeper understanding of the cosmos and our enduring quest for knowledge in the face of the inevitable march of time. White dwarfs are not just dead stars. They are the key to understanding the entire life cycle of stars. They are the building blocks of cosmic time, allowing us to measure the age of the universe. They are the protectors of life, shielding us from the dangers of a changing cosmos. And they are the laboratories of fundamental physics, pushing the boundaries of our knowledge with their exotic states of matter. White dwarfs are more than just stellar relics. They are the threads that bind the past, present, and future of our universe. And as we continue to explore their mysteries, we unveil the story of our existence, written in the cold embers of dying stars.